Hello and good afternoon. A very warm welcome to the ATMRI Symposium on the Intelligent Airport-Airside Management. My name is Samir. I'm your host today, and I will be looking after you and the speakers in this interesting exchange of ideas. So as we all know that the airports are the source and sync nodes in any air transportation network. And any bottleneck or inefficiency at any airport in this network can lead to major delays and congestion and can propagate thousands of miles. Especially at the large airports with complex runway configuration, multiple terminals, there is a need of efficient airside circulation to better connect the gates and the runway to fully realize the runway capacity, gate utilization, effective taxiway routings, as well as associated processes. This is also related to the new initiative of the green airports, where the growing carbon footprints of congested airports have exacerbated environmental concerns as well. For airlines as well, an effective airport airside management is very important to manage their fuel burn and also to improve their operational efficiency. Now, in recent years, as you all have witnessed, AI, specifically machine learning, has demonstrated immense potential in improving the level of predictability, safety, and efficiency in the airport operations, airside operations. So today we have a very impressive lineup of speakers from EUROCONTROL and Air Traffic Management Research Institute at NTU Singapore, who are going to share their innovative research and development on the intelligent systems for airport airside management. In this symposium, the highlight will be to see the challenges faced by the future airport airside management and how to bring the human and machine intelligence together to better manage the complexity of such a system. So without further ado, first I will request Professor Wu Dong, the Director of Air Traffic Management Research Institute, to welcome our speakers from EUROCONTROL and ATMRI and formally open the symposium. Professor Wu.
Yeah, thank you, Samir. This is a great pleasure for me to open up this symposium, not only because of a topic, but because of the contribution and the participation of my two sides of my heart, left-hand side and right-hand side. The left-hand side is EUROCONTROL, where I spend quite a lot of my time over there, and then at the right-hand side is ATMRI and NTU, where I am now. So this is my pleasure to see how we are coming up together and to talk about a very special topic, but very important topic of the airport airside management. I think a long time ago, one of our dear and honorable colleague, Dr. George Donoghue from the FAA and then from George Mason University, he stated that capacity is concrete. Concrete, that means the runway. So that means that any delta throughput that we can gain from an airport is a delta throughput, is a delta capacity we gain on our network. So I think that is really important. We have been struggling a lot with this because what we have done in the past is really we use some assumption that is not really realistic in real life. So this time with the arrival of AI, and then with the concept of AI-assisted human or hybrid AI-human working together in the team, we do hope that we are going to do to gain a lot more delta in the capacity or delta in the throughput. Okay, so our current situation is that not only the capacity or throughput that we have to gain, but also the question of sustainability and green environment. I think we have double objectives. And more, again, this is something that is really challenging for all of us. Welcome, and I wish you a fruitful discussion and so on and so forth, okay? Thank you so much for participating to this symposium. Give back to you, Professor Amir Samir.
Thank you, Professor Wu. I will just briefly go through the agenda. So first, I will give a brief introduction about the Artificial Intelligence and Data Analytics Research Program at ATMRI. That will be followed by our first speaker, Robert Graham, who is the head of airport operations at EUROCONTROL, who will be talking about the optimized runway spacing delivery through a dynamic departure indicator tool. After that, there will be a presentation from ATMRI from Dr. Thin about learning-based approach for reducing taxiways delays, and then followed again by EUROCONTROL. Mohammed Al-Jimi will be, who's the airport research project manager, will be talking about the reduction of the aircraft separation and dynamic runway time prediction. This will be followed by next presentation from ATMRI by Li Long, who will be talking about the deep reinforcement learning approach for real-time departure slotting. So at ATMRI, we have embarked upon this very ambitious program about using human AI hybrid approach for developing these 4 streams leading to a next generation of air traffic management system. These 4 pillars in this program are on trusted AI ecosystems so that we can develop machine learning algorithms which are explainable and can be trusted by the users. So this is the fundamental spirit of this particular project. Then we have data-driven airspace optimization, where we formulate the problem of airspace capacity, airspace safety as a machine learning and data-driven problem. So this particular project looks into airspace optimization from a machine learning perspective. Then we have the Airport-Airside optimization project. This is the main part of the presentation today, where we are talking about optimizing the airport-airside, including runway, taxiway, and gate operations using machine learning methods. And last but not the least, we have conflict prediction, conflict detection and resolution as a machine learning approach. So this is topics that we'll be covering in our next symposiums in future. So with that, I will now come to our first speaker, Mr. Bob Graham, about optimized runway spacing and delivery through a dynamic departure indicator tool. First, a brief introduction. Bob is the head of airports at the EUROCONTROL, and he has been tasked to integrate airport into the European ATM network manager and to support the local airport operations. He has also worked with the European Commission, where he has supported the development of the first European single sky legislation package, as well as the single European sky ATM research program, where he later worked at the head of concept strategy and development. So Bob, over to you. We look forward now to your presentation. Thank you.
Thank you very much, Samir, and thank you very much to Dr. Vu Duong, a great friend from time EUROCONTROL, for your introduction. So I thought I had my slides up, but here we go. Let's put them up, and I hope that I'm sharing them correctly now in the right mode. And not wanting to start at the end. My apologies. Okay, there we go. That's better. So if you can just confirm that you can see my slides in full mode. Great.
Yeah,
Thank
go ahead.
you very much. Okay, so a great introduction. What I'd like to try and do this morning is, or this evening for you, is to give a 4-step view, just a little bit on COVID, because it's such a big change, game changer to us. The second slide, just underline a little bit where this work situates, give you an overview of work that we've done, which would be detailed more by Mohammed. So we're both contributing and complementing each other. And then getting to something which we call the dynamic departure indicator. Now looking at how we can squeeze more out of the departure runway. So I think it's really important to cite that I had the experience of working with some of the students at the university, and ATMRI is really taking a big picture approach. It's taking a system approach, and it's got building blocks for each one of the different areas that we're looking at. And I think that's something that really has to be taken at this moment in time, just simply because the interactions of the different areas and different blocks. So what you're looking at here is a weekly traffic evolution. We do this every week. We're continuously updating the traffic situations and the impact in Europe, but this tells the whole story of what happened from the beginning of lockdown around about March of 2020 all the way through to now, and it's really quite dramatic, and I think you've seen your own versions of this. And if we take a slightly closer look here, You can see we started to get a peak around about December time, so the Christmas holidays. Europe wasn't quite so badly impacted, but we're now into this terrible phase of a third, and in some countries, even a fourth lockdown. And if you consider that our traffic throughput is roughly about 36,000 movements a day, at the moment, yesterday's traffic was 11,700. So we're really hit in quite a big way. This little slide here is giving you a bigger view, so we track what's happening internationally. This is primarily about the international flights. So again, it's a really bad picture. And in fact, as we look forward to how things are going to improve, on this slide, you can see on the right-hand side a number of scenarios. EUROCONTROL is pushing on the green one, which is about a partial improvement during Q2 of this year. We're already above that, but it's falling back again, primarily because of challenges that governments have in terms of allowing people into the country and those really draconian restrictions that are there. So this is what we're looking at. And our hope is that coming into summer of this year, we're going to get into scenarios of between 50 and potentially even 70% of 2019 traffic. And that is going to pose everybody a lot of problems because the staff is no longer there. The staff that is there is not necessarily up to the standard of high peak traffic. So there's been a lot of regulation, and I'm sure there'll be a lot of delay, unfortunately, inside the system. But that's the point when people start to get the confidence to come back. And what are they going to come back to? Well, everybody talks about the new normal, but nobody tells us what that new normal is. And I think that's one of the big challenges we have as we're looking forward from an academic or even from a planning side, from a network manager. But there is change. So our thinking is that a lot of the traffic come back will probably be mostly low cost, much more regional, limited in terms of international, until governments start to really open up their countries. And what this means is, building on what has happened in the COVID crisis, the change that we're going to be seeing, I'm pretty sure, is people have been used to hearing no noise. They've been used to hearing about improvements in the environment. So there's a little word that I put in there, which is called sustainability. And sustainability is something which is really going to underpin everything that we're going to do. Those expectations are that we're moving into a better world, hence my little green change graphic. So we need to get into a sustainable recovery. And what I mean by that really is that the business of air traffic management, of airports, of airlines is going to have at its core sustainable evolution. So our business motivation is going to change. And that's not something we can do overnight. It's a lot of investment, a lot of research has to go before we get into that point. But certainly an efficient aviation built on sustainability is the way forward. So if you keep that in mind now, for all the presentations, you'll be seeing that what we're trying to do is to eke out improvements that bring efficiency at a level of cost, but bring additional throughput. Where we're behind the scene is, how do you make that sustainable? Okay, so if we're going to push more and more aircraft through a runway, is that going to be something that is a sustainable situation? And you can see the picture on the right-hand side. That's typical of what happens when you get into a peak period. Lines of aircraft waiting at the runway to take off, burning fuel, dumping carbon, and all sorts of things that people are no longer happy with. So this was our before COVID scenario. We were looking at continued traffic growth in the ECAC area with a significant view that by 2040, we'd have about 16 airports in that area that were looking like Heathrow. Okay, now Heathrow is peaked out from the moment it starts in the morning about 5:30 through to about 6:30 until when it closes due to noise at night. So noise is a big issue, peak traffic is a big issue. And if you've got 16 of those in the European area, we will have a lot of challenge to the network. And we will not be able to meet all the demand. So we started to look at different ways of doing this. And Mohammed will give you maybe a bit more detail on it. But some of our first issues were, can we change what has been in ICAO for years, wake vortex separation, separations on final approach? And we came up with the recategorization, working with our international partners, including Singapore, Hong Kong, Dubai, Japan, and the United States. We came up with this new recategorization, which is now enshrined inside the ICAO world since October of last year. And then some tool sets to help the controller, such as time-based separation. Time-based separation from Europe was brought along to resolve an issue of wind mitigation. But in fact, by itself, it is a predictable delivery tool that provides additional throughput irrespective of the wind. And these are some of the core things that I'm going to walk through because they taught us an awful lot about how we can improve our departures. Now, two things to retain here. Final target distance, FTD. That's when we want to make sure that a separation is delivered. And initial target distance, ITD, that is the point at which we want to position the aircraft to make sure that in the last 4 miles of flight, the compression as the pilot prepares the aircraft for landing, reduces speed, starts to deploy flaps, puts the gear down, is getting the aircraft in a point when the speed is dramatically reducing. You're thinking of profiles typically at most airports from 50 miles out, from 210 knots coming down to 180 knots, coming down to 160 knots, and then round about 135, 140 knots on final approach. So the aircraft in front of you, the leader, and you're the follower, is at a moment in time beginning to configure and to slow down. So therefore we have these two distance indicators so that by the time the aircraft reaches the threshold, the actual simulation separation has been achieved. So I'm really wanting to keep that because we've stolen this idea for departures as well. And when we calculate those final target distance, the computation takes into account a number of different things, such as the wake vortex, aircraft type, weather conditions, the minimum radar separation that is allowed, and the runway occupancy time. So this is complex, and hence the need for a tool. The controller has been calculating this for years, but as you start to tighten this down, these separation minima, you really need to have a system support that is helping the controller to achieve that. So if you've got the thing right, when the aircraft crosses the threshold, that computation will have been done in the correct way. And same thing for the initial target distribution distance indicator. It's really about pulling all of these different things to make sure that as the aircraft is flying down final approach, the system has calculated the notion that around about 4 miles, that compression effect will start to take effect, and the aircraft will reduce their separation to the required minimum. Now, we make it a bit more complex. So we looked at time-based or even distance-based, and here we're translating the actual laid down separations into a time, which means that you could have aircraft flying at below the distance, but it's mitigated, for example, because there's a strong headwind. So typically in a low headwind, 5 nautical mile might be your spacing requirement, which is 122 seconds. When that wind increases, the system would reduce the separation indicator to the controller, and therefore you'd get still the same time, but the distance between the two aircraft are reduced. And that's quite a complicated calculation, which is where we started to do our first AI work, looking at the buffers, looking at the distance to fly, and the different calculations and data that we had to see actually how you could reduce that in a safe and efficient manner. This looked very much as an example we have here, the speed model, trying to work out what a lot of data was telling us, then applying AI to actually see whether our statistical analysis could in fact be refined. And indeed, when we looked at the buffers that we were applying, we were able through AI or machine learning to significantly reduce the distance, therefore getting additional throughput gains. Now, I keep going on about our throughput, and I'm afraid I will not be telling you what the nirvana would be about what that means in terms of sustainability. I'm afraid that's going to have to be the next thing in terms of our research. But certainly at the moment, we're not solving that sustainable equation. So you can see from here a number of things that have happened. We've looked at a speed model. We looked at the traffic mix. We've come up with terms such as leader, follower. We've improved the wake vortex. We've begun to use time. And in that mix, we started to use AI computations to refine it down. And that methodology has been applied to what we call the dynamic departure indicators, DDI. And that's what I'd like to get into now. So if we look at departures, the controllers and the researchers amongst you should already have broken down to really what we mean by a departure, even what we mean by an arrival. So you can have a distance based or you can have a time based. Typically, an aircraft takes off, it crosses a particular point, and the controller from its local regulations is allowed to give the next aircraft a takeoff. That could also be an altitude. So the aircraft takes off, crosses 2,000 feet, and at that stage you're allowed to let the next aircraft go. Or it could be a wake's vortex, where you've got a heavy leader and the follower being a medium type, in which case you're going to apply a time separation. And this is managed by the controllers today. The question is, if you could start to systemize it, bringing in some support, could you get the same sort of benefits that we're getting on arrival on departure? And the answer is yes. You can get some significant, in a segregated mode operation, anything between 5 and 10% improvement. And in a mixed mode, you can get something about 2 to 5%. And that equates to mixed mode 1, maximum 2 movements an hour, and in segregated mode, even up to 4 movements an hour. And the mix here that we look at in terms of the distance space, you can see there is again the same sort of things. Minimum radar separation, the vertical separation in terms of how quickly an aircraft is going to climb. Something which is really important, which is the reduced runway separation, which every airport has its own versions of, depending on its local traffic configuration and local runway layout. And importantly, the standard instrument departure. All of this going into the machine learning pot to try and actually find out how we can use the data that we have collected from these different configurations to come up with the indicator that allows the aircraft to take off with a safe separation. And then, of course, there's the wake separation and any other local values that we have. So to help the controller, we have this notion of 2 dynamic departure indicators. One is expressed in distance, so nothing's new there, and one is expressed in time, nothing new there. But what is different is that behind this, we have a lot of data which is driving the actual decision-making to be able to refine that. So when an aircraft is taking off, you're lining up the next one to go, then there's a system support giving the controller a countdown as to what time that a safe separation has been achieved for the cleared takeoff message to be given to the pilot. I'm going to walk you through 2 of the examples, okay? So here, if we're looking at the time-based, this is an example based in altitude, and we have a clock. The aircraft is given clearance to take off. They start their takeoff roll. You can see the second aircraft is lined up. And as we're moving along the time frame, the countdown is beginning to go down to 0, which allows the following aircraft to take off. And the aircraft starts to take off its roll. Now, one of the things which is actually really important to mention here is, in fact, there is a delay also from the time a controller tells the pilot you're cleared takeoff. The pilot has got a number of checks to ensure they're trying to get that done before they're lined up and they're ready to go, but there's still then even a human delay inside that. So the system has these built in. As we had buffers for the arrival separations, we have buffers for the departure separations. And therefore, using this system, the departing aircraft reaches its delivery point in altitude, and that distance-based separation has been satisfied between the leader and the follower. The second one is a separation minima where we're going to look at a marker. And typically this would be used where you have a geographical separation, such as a split in the standard instrument departures. Typically, aircraft will climb straight ahead for an altitude, and then they will be allowed to make a turn left or right, depending on the geography of the airport and any other sort of constraints. And at that time, you get a split, which is how controllers work today. And based on that split, you're allowed to give the second aircraft a takeoff if there is no other constraints, such as wake vortex or a specific time if they're going to follow each other into an exit point in the airspace, which may have been required by the departure controller and radar or the en route controller. So in this case, there is an indicator that's been identified based on the multiple constraints. The pilot is given takeoff. The leader the follower lines up. And then once that physical marker has been cleared, the controller gives the next aircraft clearance to take off. All of this is usually done by time, but it may be that the marker is now, in this case, indicated to the controller on the radar display. So what's new? Why are we teaching you to suck eggs? We know how it works. We've been doing this for years. Well, in fact, the new bit is data, digitalization, breaking this down into the different aspects of work. There's a rolling distance, there's a rolling time, there's a reactionary delay. The aircraft has to wind up its engines to start its roll. There's a time to travel. If you remember the speeds that we were looking at on final approach, in this case, we have a time to travel. There's a notion of the acceleration point, and then there's a time to fly. And again, if you think about these things, a controller today is already mentally doing gymnastics and working out how all this works. But now we say, well, we have this data. How can we actually optimize it? So from statistical analysis, we come up with this sort of sequence of different approaches for the computation to be made to give the right time and to give the right distance marker. Now we put in the notion of AI, and that data is now refined, taking all the data elements that are available and starts to produce a more refined indicator in the different areas. You know, what is the most appropriate wake separation stroke minimum radar separation, so SID stroke vertical separation configuration. And then we provide that back to the controller on the basis of a human machine interface so that they can deliver the separation. Now, I'm not going to get into the data work. I'm not the expert here on that. My background is more operational. But you can see that we've been taking that data, working it through, and then trying to find out what the different components actually look like so that we can use them in our computational model. So the two examples here that you're seeing is either using radar data analysis, and today ADS-B is also something that we use, or the Mode S data, which has been provided by the aircraft to come up with the different configurations that the system needs to use to do those calculations. So finally, as I start to draw towards an end, we've got to a point where we've run this now in two different simulations, one with Charles de Gaulle, and the other one, which you're seeing here, is Vienna. And in Vienna, the traffic mix there is much more of a medium type with around about 10%, I think, of heavies. And here on the left-hand side, you're seeing the approach to having the timer. And in that timer, you see the leader aircraft and the follower aircraft, the sort of information the controller needs. So the controller is still building a situation awareness. But what is new now is, in this case, they're given a time of 84 seconds. It's not 1 minute, 2 minutes, 3 minutes, it's 84 seconds. Everything in that calculation has been taken into account to provide the controller with a similar sort of information that they're used to when they're doing their normal separation. And as the clock ticks down, the aircraft is lined up, the separation is established, you get down to 0, and then the aircraft is cleared takeoff. And it's exactly the same thing with the notion of that marker. You can see a Speedbird 677 Alpha that's taking off, and it's going to split. So the marker's been put at the point at which the system's saying the separation can be achieved. It's as simple as that, or is it? So one of the big deals now that we've made is this world where we move into AI, and where AI can actually start to reduce and improve the systemization and the separation minima, optimizing a very scarce resource, which is something called a runway, which is at the beginning and the end of each journey. And you can see that journey from two sides, takeoff to landing, or from the gate to the runway, from the runway to the gate. And today we're going to be seeing a lot more about that part, that land side. So you can see we've had some success here. We've got some numbers coming up. It's providing safety because we reduce the amount of inefficient separation minima and the number of significantly, roughly about 10%, if I remember, underspacing, which is getting close, not necessarily to a loss of separation, but potentially. This has been primarily done in segregated mode because, to be honest, it's easier. But now the big challenge is what happens when you look at all of what we were talking about for the arrivals and you try to mix that with the departures and you get into a mixed mode operation. And of course, prepare implementation. Research is not of any value to anybody unless we can actually prepare as we're going along to be ready to help the stakeholders move such things into implementation when the time is appropriate. And with that, Samir, I hand it back to you, and thank you very much for the opportunity to present some of the work that the team is doing.
Thank you, Bob. Thanks a lot. That was very insightful of you. Please, all the participants, I would request you to post your questions on the Q&A. And in the end, we have around 15 minutes where we will have some discussions. So please feel free to post your questions, and we're going to take them up at the end of the symposium. Thank you so much. That was very interesting. Now, our next speaker is Dr. Tin Pham. Thin is the Assistant Program Director for the Air Traffic Management Research Institute AI program. Thin obtained his Master's in Computer Science from Telecom Paris Tech in France and a PhD degree in Computer Science with the specialization in Artificial Intelligence from University La Sorbonne, Paris Science and Letters. He is currently a research fellow and the team leader of the Airport-Airside optimization team. And his research interests include deep learning, multi-agent reinforcement learning, and application of AI in air traffic management challenges such as surface movement management, conflict detection, and resolution. So Thin, over to you.
Thank you, Samir, for your kind introduction. So I hope that everyone can hear me clearly. Okay, let me share my screen. Okay. So my talk today is about the learning-based approach for reduction taxiing delays. As Samir and Bob have already mentioned that for the future, right, we want to increase the capacity of the airport. At the same time, also try to minimize the taxiing delay and fuel consumption. It is one of the very strong impact on the environment. So for this talk, I have five things. The first one, it will introduce the problem a little bit. Then we go for problem formulation. I will have mentioned two of our ongoing work in ATMRI right now is the data-driven surface movement simulator, and the second one is reinforcement learning for departure metering. And finally, I go for conclusion. So for the airport surface movement, so to put it simply the airport surface movement problem is the routing and the scheduling problem, in which we try to navigate the aircraft from their position to their destination in a timely manner, while trying to optimizing the overall cost and resources like the fuel consumption, the gas usage, etc. It's a complicated problem, and in which we have a lot of different sub-problems like taxi route assignment, pushback control, or departure metering, departure sequencing, runway sequencing, etc. So in this talk, we only focus on departure metering or pushback control by trying to reduce the taxi delay and fuel consumption, because it's one of the, like we mentioned, one of the important problem for any airport. So the main challenging here is that any airport is a complex system with several time critical process, actor, and that leads to a lot of interaction and uncertainty. So how we can handle this one? So now we go with the departure metering. What is departure metering? I have mentioned before. The departure metering is a surface management procedure in which we try to hold the aircraft at the gate when for departure aircraft at the gate, rather than let it go on the runway and wait and have the correction and wait at the runway or the wait at the taxiway or the runway holding queue. So by doing this one, the whole idea, the motivation is we try to shift the waiting time of the aircraft from the taxiway with engine on to the gate when the engine is off, and we save the fuel in that way. So as you can see, the benefit is have four things. The first one, you can reduce the aircraft waiting time at taxiway and runway queue. Secondly, we can reduce significantly the fuel consumption. And we also can improve the passenger experience with the smoother departure flow. And finally, last but not least, we can reduce the workload of controller by reduce the compression on the surface movement. On the left-hand side, you can see the demonstration of the departure with and without departure metering can be affected on the runway queue. So one of the most difficult thing here is how we can model the surface movement system. In the future, when we have with the more technology can apply for during the taxiing process, we can have the human automation taxi system in which we can have multiple different type of taxiing technology. So it's this to one of the most challenging things here is how we can accurately predict the position of aircraft and the taxi at the same time the taxi time for all the aircraft in the airport. So without the good accurate prediction, so it can lead to a lot of uncertainty and inaccurate that can affect the performance of any optimization algorithm. And as I show on below, right? So given the same taxi route, we can have different taxi speed profiles and taxi time for each aircraft. So the uncertainty on the surface movement and simplification on the model of the taxiing trajectory can have a strong effect on the performance of the departure metering policy. So one of the main things we will do here is how we can target this problem. So the research question is we try to use the deep reinforcement learning for tactical departure metering to efficiently reduce the aircraft taxiing delay. So here the input will be the schedule when we have on the taxi route, assigned taxi route, and also the milestone like the target upload time, target takeoff time, etc. The most important thing here is we also want to have the high accuracy predictive model for taxi time prediction. So that's the reason why in this talk I will mention two our research, ongoing research. First one is on data-driven surface movement simulator, and the second one on deep reinforcement learning for departure metering. So first one for data-driven surface movement simulator. So here I present two things. The first one is to develop that one. We go with the idea of develop an integrated surface movement simulator, in which we try to integrate the arrival manager, surface manager, and departure manager together to have the smooth transition for aircraft from gate to runway and vice versa. So at this one is the basic. We also need to develop a lot of algorithm and algorithm to handle the traffic, like route recommendation, conflict detection, resolution, trajectory prediction, etc. So at beginning, this one can be go with the classical approach for building on the building block here. However, each of this one will be enhanced by machine learning later to increase the intelligence of the simulator and make it more realistic. So one of the first talk today is how we can model the trajectory, the movement of the aircraft in the airport to make it more realistic, and somehow it can reproduce the real scenario in our simulator. So to do that one, we use the idea of generative adversary imitation learning. As you can see on the architecture here, so we use the idea of generator and discriminator. In this one, we use the real data, the real movement data from AMGCS system to model the movement of the aircraft in the airport surface. And then the purpose of the generator is try to mimic the behavior of the aircraft by controlling aircraft from gate to runway, for example, and mimic the behavior from the data. The purpose of the discriminator is try to distinguish between the real data and the generated data. So at the competition game, right, both of them will play together and improve themselves. And after the training, at the result, we will have the generator model that can control the aircraft successfully from gate to runway with the behavior somehow similar to the pattern we can observe from the data. So to do that, as I mentioned, first we develop the simulator. We call here the environment that can have to control the aircraft from gate to runway. And then we will plot on the historical data at the surround traffic and use it for training and testing. The control action here will be used at the acceleration. We use acceleration to control the aircraft. For the feature, I think that here effectively we have 4 group of state feature. The first one is the feature related to the flight plan. For example, the aircraft takeoff time, target takeoff time, or target startup approval time, etc. The second one is the flight status, is the current information about the speed of aircraft, acceleration of aircraft. The next one is the taxi route feature. It's related to the taxi route characteristic of the flight, such as the turning angle, whether this area is high speed or the low speed area, etc. And the last one is the traffic feature that related to the surround traffic, of the information of the aircraft, like whether it have a conflict, any conflict ahead or the traffic density. Okay, now we talk about the result of our model. So after training and conversion, our model can somehow generate realistic movement, which can observe from the data. On the left-hand side, you can see some of example of generated speed profile. The orange one is the speed profile generated by policy, and the blue one is the actual data. So even though they have some slightly different, however, the behavior on acceleration and deceleration to handle the traffic is somehow matching, is very similar. And on the left-hand side, on the right-hand side, you can see on some statistical analysis on the movement pattern at different type segment. So here we have two type segment, the turning segment and the straight segment. So as you can see with the orange one for the policy and the blue one for actual one, the pattern somehow similar. So for this one, we can conclude that our model can generate the realistic movement similar to the behavior of the aircraft in the data. So the second thing, also the most important thing, is can it estimate the taxi time correctly? So we use the baseline model. We use the aircraft speed to control the aircraft. The aircraft speed is derived from the average speed of the traveling taxi segment that we can do the calculation based on historical data. And we do the testing on different data sets with different like minimum travel time. And at the result, you can see our model can provide a very wide, robust result with less than 50 seconds root mean square error compared to the baseline model with much significant error. And also it's in the baseline model, you can see the increasing of the error when we consider the longer travel time scenario. However, in our case, it's quite stable. So at the conclusion, this one, the model is somehow successfully imitate the aircraft movement pattern and estimate accurately the aircraft travel time. So this one will be integrated in our surface movement simulator later for training and evaluation the other algorithm we have, especially, for example, the departure metering policy. So that is for the simulator. So now we talk about the reinforcement learning for departure metering. So recall about the markup decision process we have shown before. So in this one, we have two things. The first one is the policy. The policy to make decision whether we hold or release the aircraft based on the current situation, whether it's better to hold the aircraft to reduce the congestion or delay, or we should release it right now. If not, it will be late, for example. And the second one is the simulator environment, in which we simulate the traffic. For each action we have for policy, we need to simulate and estimate how it's going on in the environment if we execute that decision, right? So this means the simulator is also one of the important things here. So for that one, we need to extract a few features from the environment as the state representation for observation. So here we combine the global feature at the airport level and some of the local feature for the aircraft specific feature like gate, runway, or travel taxi, travel distance. So this is the markup decision process for our problem. For this one, at initial stage, we work with the abstract environment, airport environment. So as you can see on the left-hand side, it's the abstract airport environment we are working on right now with the approach, the two runway, and then the taxiway. So here the red one is the departure and the blue one is arrival. So we given the schedule with the assigned taxi route and milestone. And then here we don't consider about capacity of the approach. However, as you can see, I must want to note that this one, all of the parameter, all of the assumption can be described from the data directly. And I will discuss about that one later when we move to new airport environment. For training, we are using one of state algorithm for reinforcement learning. We call it the BPO, proximal policy optimization. The first one I want to emphasize is the episodic reward we are using. So here we have three reward. The first one we call penalty for the gate, the taxiway, and the last one is the big reward when it reaches the runway. By design this way, we want to encourage the agent to hold the aircraft at the gate more than the delay on the taxiway. So by minimum and maybe it's the same like time T. However, when you shift the delay from taxiway to runway, taxiway to the gate, we can reduce the penalty and increase the reward. So for training, we will train for single agent setting. It means that at each training, we have control one agent to do the training, control the aircraft for holding or release. For evaluation, we will copy that policy for all the agents and use that one in the multi-agent setting for evaluation for evaluating the performance of the model. So for the observation here, we can see we show the scenario with 15 aircraft, 9 departure and 6 arrival. We control all of the departure here. On the left-hand side, without measuring, we can see the congestion on the taxiway and the density long queue on runway. However, on the right-hand side with the measuring, we don't see a problem. So for the simulated environment, simulated scenario with 40 aircraft per hour, we observe that our algorithm can reduce the total taxi delay up to 25%. And for the average taxi time saving, we can obtain that, okay, it can reduce, the saving can go up to 50 seconds per flight. Especially when we increase the traffic density, we observe significant increase in the departure metering benefit. So for example, when we increase the number of aircraft from 30 to 70, the average taxi time saving increased 10 times from 23 seconds to almost 250 seconds. So it's a significant improvement. At the same time, the average gate holding time is at around 7 minutes, still stable. So our ongoing work now is adapt the current work to the changing airport environment. And our idea, we try to combine the two mentioned research to have the departure, the deep reinforcement departure metering on the data-driven surface movement simulator. And with the current work, for the initial result, we observe similar benefit for departure metering. However, some more experiments should be conducted later. So we will update the result for you in the next conference. So for the conclusion, so here we have two things. The first one, we want to mention that machine learning is a potential solution for model the complex surface movement problem. It can, and our model have demonstrated it can imitate the aircraft movement pattern from data, estimate correctly the taxi time for the aircraft, given the surrounding traffic, and later on we can enhance the simulator with the conflict detection resolution algorithm. The intelligent pushback control is important, and it can reduce significantly the taxiing delay. We can relate to the fuel consumption or operational cost. Our approach is, I can say that our approach is very easy to adapt to any airport environment with the limited expert input or calibration. And for the next work, we think that delivering aircraft to the runway queue at a timely manner will be considered and it add into our research. So I think that's all for my presentation. Thank you.
Okay, thank you so much, Dr. Thin. That was quite insightful use of machine learning in predicting the aircraft spatio-temporal trajectory at a given airport and to use it for departure metering. Thank you so much. We'll have some questions. So please keep your questions firing. I can see lots of interesting questions coming in. We're going to talk about them towards the end of the presentation. Now we have the next speaker from EUROCONTROL, Mohammed Al-Jimi, who is the airport research manager, project manager at the EUROCONTROL. Mohammed was awarded the engineering degree in aeronautics and computer science from the INAC, the French Civil Aviation University in Toulouse in 2000. And he also received project management and certification from the UK. He has over 20 years of experience in air traffic management. Muhammad's research focused on airport performance optimization, and he has been working for several years in the CISA program, looking at different airport topics, including routing, safety nets, airport guidance, virtual and augmented reality applied to air traffic control, as well as runway management. Muhammad, we look forward to hear from you on reducing the aircraft separation based on MR standards revision and dynamic runway occupancy time prediction. The floor is yours, Muhammad.
Thank you, Samir. Good afternoon, everyone. I'll share my screen.
Go ahead, Muhammad.
Okay, so I will build on what Bob described as work that we did for the last decades on RECAT and the pairwise separation. So when we elaborated this table of 96 by 96 on pairwise separation, we noticed that the limitation that can be seen for reducing the separation is mainly divided into categories. So the first one, which is the MRS. Today, the minimum radar separation as described in the ICAO 4444 is 3 nautical miles and can be reduced to 2.5 under specific condition. We know from experience in Heathrow, for example, that delivery of 2.5 nautical miles for DME can allow us to have a delivery of 2 nautical miles on the runway. So 2 nautical miles is safe. And then we said, okay, why not we study how we can implement 2 nautical miles, and we study the required surveillance performance for reducing to 2 nautical miles. So what we did is that we studied the separation minima structure. We focused on what can be produced as a technical requirement for the surveillance minima. And then we had some exercises to see the impact of reducing to 2 nautical miles on the work of the controller, on its workload, etc. So we did some real-time simulation on Vienna environment mainly, and I will show you later on the results. So once we reduce the minimum radar separation, the other factor which becomes the constraining factor to reduce the separation on arrival is the ROT. So the second side where we can do some reduction is by predicting the correct ROT. So the ROT, as stated before in the previous presentation, depends on different factors also, such as the aircraft type, the runway configuration, the runway status. It depends also on the weather condition. So some buffers is added to take into account this ROT. And what we said is that, okay, if we have from the ICAO the 180 reference speed that allow us to compute the 2.5 nautical miles, why not we apply exactly the same thing? So this reference speed to obtain the distance that corresponds to the ROT. So for example, if we have an ROT of 55 seconds, then we transform this to a distance which becomes 2.75 nautical miles. And then we can put in place a similar table to what we did before on RECAT. We do a new recategorization of aircraft based on the ROT. So first, what we proposed is what you call ROCAT categorization based on ROT in a procedural scheme. So simple categories based on analysis and studies of the ROT can allow us to produce such table. So for example, if I take this blue line for the medium, we can see that we can have for low ROT one category that allow us to reduce the separation for those particular aircraft. So this doesn't need an implementation of a tool or a pairwise separation scheme table. The second one is a more advanced one, because here we take into account the type of the leader aircraft, and then we can go into more refined separation. And in this, we need to have a tool. This is what we call the ORD tool. It's the same tool that Bob described in his presentation, but here improved with this functionality of ROCAT. So we, after elaborating the concept, we did some simulation. The first one was with Zurich Airport, where the ROT is a very constraining factor in the separation. And we did also the same thing with Vienna. Here I will give you some insight of what we did on those simulation and what we developed as tool. And I will come to the need for the machine learning and the artificial intelligence later on. The ORD tool, what we call the LORD tool, the Leading Optimized Runway Delivery tool, takes into account all those constraining factors, either the MRS or the ROT or the wake, etc. So we have the possibility to configure the tool to have an MRS of 2 nautical miles and to take into account the different categorization of the ROT plus the wake. So I will go quickly through those slides that Bob described before. This is just to show you that in the tool, we have what we call the ITD and the FTD. And the difference is the compression buffer. Here, what I wanted to add is mainly the aspects of for the arrival, what we need more for the controller to use this tool. So first, we have the what you call the LORD sequence list. So we know that the sequence of computation of the separation here, for example, we know that the number 4 after the LGL 8851 will be the easy jet, and then the chevron that we saw behind the LGL is correspond to the EasyJet aircraft. The tool also is taking into account the fact that the aircraft can be in a position after its ITD. In this case, an alert is raised to the controller to warn him of infringement of the ITD, and this is a possible separation infringement if the controller doesn't take an action. Second type of alert is related to the sequence list. So if the aircraft is not in the correct sequence, of course, the display is not correct and the controller needs to modify this manually. The last one is the catch-up alert. So when we do the computation of the chevron and of the separation, we have a reference speed. And if the reference speed, there is a big margin between the two speeds, then there is an alert which is raised. Yeah, this is the speed alert. So here an example of the traffic sample that we used for the test on Vienna for this concept. We try to mix, but also to take into account the fact that the majority of the traffic in Vienna is mainly medium aircraft. And we also did different degraded modes that allow us to test the possibility of, for example, a failure of the tool or a wrong computation, and to see the impact of this on the controller and collect their feedbacks. So here are some results about the use of the LORD tool and the change to take into account this new separation. And we noticed that the fact that we reduced the 2 nautical miles MRS allow us to increase the throughput by 12%. In another run, we had also computed the same thing. So this is the result of 2 different runs, and the increase in this case was about 22%. For the impact of the degraded mode, so the 2 modes that I described previous on, there was no impact. The feedback was very positive from the controller. So when we do our analysis, we don't take into account only the safety, but also the HP factors. So I saw one question about this previously in the chat. Here, I give you an example of the HP impact, so the workload impact of using the ORD tool and the new separation. So there is slightly, of course, increase on the workload when we use the ORD tool, but it's still acceptable. And even if we reduce to 2 nautical miles, the workload is not impacted by this reduction. So this is the interpretation of the result. For the 2 nautical miles MRS, the controller were able to intercept the final shortly then when we use 2.5 nautical MRS, and this is a significant result because for the controller, the length of the final is an indication of the workload and the task load, because the more that we have a big length of the final, the more the workload is important. So the applying of the 2 nautical miles MRS was a significant reduction of the workload by the end of the day based on this indicator. So when we did all those analysis on the EUROCAT, we did it basically on the historical data analysis, and we said, okay, we can go further and we can introduce machine learning to predict the runway occupancy time. And we can also, one of the results of the simulation is that we can improve safety if we look to other things happening on the runway, such as the runway exit. So in CESAR 2020, the program that started last year, we started working on the use of machine learning to predict the runway occupancy time and the runway exit. So here in the picture, the controller from Vienna working with this tool, and you can see the green arrow showing the exit for the controller, so that he's aware where the aircraft will exit. If we notice that there is a difference between or a prediction that the exit that it will be taken by the aircraft is not the one that was initially predicted. So we do 3 different predictions. Then we alert the controller about this, and it's possible for him to either communicate with the pilot to know exactly what is the runway exit, or to change it manually. So we are doing 3 different prediction. One an initial one at 10 nautical miles, and then we improved it later on. So I'll show you the result of improving and changing this prediction in the next slides. The EUROCAT concept is also investigated by Airbus in CESAR 2020. So the aircraft will be able, in this case, to predict based on machine learning the ROT. This ROT can be downlinked to the ORD tool, so that now we can have a better view of the runway exit also and the ROT coming from the aircraft itself. So two separate projects for the moment investigating this ROT prediction and runway exit prediction, and we are collaborating with each other to see the result and the way how we can work together to implement this from the air side and the ground side. So this is the first results of what we did when we used the machine learning in the case of the Zurich airport. So we had 3 years of data from Zurich, and in the next slides I will show you the configuration that we set up. So we had a first prediction at 8 nautical miles, a second one at 2 nautical miles, and the last one at the threshold. The 10 minutes setup, we modelize as a regression problem where the target is the ROT. 2/3 of the data was dedicated to the learning and 1/3 to the evaluation. And the result is shown for the feature that are the most important for the first prediction. So the runway and then the airline, then the aircraft type. In the short term setup, we added some other feature like the ground speed at 2 nautical miles. And we improve also the prediction thanks to some feature like the weather feature. Here is the improvement compared to the baseline. So as you can see, there is clearly an improvement when we use the machine learning compared to the baseline prediction. And mainly for the case of Zurich, we saw that this is mainly for the runway 14. And for those of you who doesn't know Zurich Airport, the runway 14 is really dedicated to arrival and has a special configuration. So the ROT is a very important factor on separation for that runway. So again, some feature importance that shows that the runway is still the most important one, then the airline, and now the speed becomes very important. And at the threshold, the speed becomes the second most important criteria. So the result from using machine learning is that it can support the development of accurate modelization of ROT and computation of the separation. The prediction when we go to the short term is, of course, much better. And then one of the most interesting results is that we can use the different 3 prediction in different manner. So for the one at 10 minutes, it's mainly used for the separation and the display of the chevron. For the 8 nautical miles, the indicator for the FTD can be improved using this computation. And at 2 nautical miles, it can allow us to have the alert. And this is mainly for the runway exit alert that I described before. So the conclusion from the different simulation that we did and from the work that we did using the machine learning, first regarding the MRS, so the reduction to 2 nautical miles MRS was well received by the controller and showed very good improvement in terms of separation and runway throughput. For the RUCAT, same conclusion also. The controller were able to work safely with the new tool. And we had very good improvement of prediction when we used the machine learning techniques. The next step for us, we will do live trials using machine learning in Copenhagen, we hope in September this year. This trial, of course, had to be changed from April to September because of the COVID. We maintained now, and we hope that this will take place. As said by Bob before, we will look to different configuration because for the moment we are more concentrated on segregated mode, either for departure or for arrival. Also one of the most interesting step is the integration between air and the ground of the different concepts. That's all for me. Thank you very much.
Thank you, Mohammed, for such a fascinating insight. I'm sure that when we are next have the opportunity to fly, and when we are landing on a runway, it will be a reminder to all of us how precious resource we are going to land on. So it was interesting to see how we are moving from time-based separation to distance-based separation towards machine-learned separation. And I'm sure that with machine being able to approximate the various complexities in the system, there will be a dynamic on-the-fly separation available to the controllers, which they can apply. And that will improve the runway capacity significantly. Now, our next speaker is Mr. Chan Lee Long. Chan Lee Long is an aeronautical engineer graduated from NTU. He is a project officer at the Air Traffic Management Research Institute. Lee Long is a gifted machine learning scientist. And the fact I can testify because his undergraduate assignment as an undergraduate student was published in a top air traffic journal, Journal of Air Traffic Management. So you can imagine someone as an undergrad can do an assignment in such a way that can be published in a top journal is a testimony to his interest in machine learning methods. So now we are moving deep in terms of deep reinforcement learning. And we are going to see how deep reinforcement learning can bring significant benefits, especially when looking at free departures in 100% arrival priority. So Lee Long, the floor is yours. Please go ahead.
Thank you, Prof. Samir. So let me just share my screen. Can anybody hear you fine? I think it's looking good. Okay, that's good. Okay, so my presentation will be on the application of deep reinforcement learning for departure slotting in a mixed mode runway. Okay, so let's start. So these are contents I'll be going through there. I'll give you a brief introduction of the problem. I'll explain more about the problem and introduce to you the problem formulation. Right? I'll then show you our simulator, and we'll end off by showing the results that we have, and I'll give you a brief conclusion to this whole problem. Okay. So airports around the world, they can choose between two runway mode configurations, right? One is a mixed mode, where the departures and arrivals share the same runway. And the other configuration would be a segregated mode, right? Where the departures and arrivals are segregated. So in theory, mixed mode is more efficient. However, it is tricky to slot in the aircraft. Because if you think about it, any mismanagement in a mixed mode operation, right, might cause even more delay than operating in a segregated mode, right? One example might be arrival might need to have go around if the wrong departure clearance is given. Okay, so to concisely represent the mixed mode problem, let's take a look at the time and space diagram that I drew for you here. So you have two arrivals like this, right? And each of these arrivals have their own separate runway occupancy time and their own approach speed, right? So there's a variance mostly in the runway occupancy time. And in between these two arrivals, right, there exists a gap shown in blue here, where we can depart departure aircraft, right, in this gap. However, we cannot just depart in any way we like in this blue color gap. There are rules to follow, right? So what are these rules? The main three rules, or in this case, will be that the departure for departure aircraft to depart successfully, right? It has to follow these three rules: departure separation, the departure arrival separation, and it must wait for the leading arrival aircraft to exit the runway before it can take off, right? And these values here, they are stochastic during operation, right? Which means they have variance and they might change with a different weather and so on and so forth. So in layman terms here, what mixed mode problem means is that how many of the orange box, right, in this case, which represents the departure separation, can we fit into the gap, right? Now it's easy to identify this in this diagram, right? Because I drew everything for you in terms of time, where you can see future information. However, it's way trickier, right, to identify this ahead of time. So what does ahead of time means? So we have the same diagram, right? And usually the future information is blocked off, right? So you should be able to make a decision to take off or not at this time. So the future trajectory of the arrival aircraft has different variances, right? And at this point, any reinforcement learning agent that you introduce to this system will have to predict the future trajectories ahead of time. Right? So one thing I would like to everybody to take note here is that while I'm saying that the agent will have to predict possible future trajectories, it does not mean that we'll intuitively know or deterministically know what the model is predicting. Right? Remember, our goal here is to predict when is the optimal time to slot in an aircraft and not to predict the future trajectory. Right? Okay. So with that, I gave you my main problem statement. Right? In a mixed mode configuration, how can departures be safely and optimally sequenced into arrivals to maximize the runway capacity? And if you think about it, a runway controller actually has to consider a lot of complex information in order to sequence between arrivals and departures. It has the different separation to consider different aircraft type, different approach speed, different rate vortex separation. So one example of processing complex information in order to make a decision, right, would be playing a video game, right? Given a screen like this, right, it does some processing based on the stimuli that it receives, and it arrives as the action. Okay, so in 2015, right, the Google DeepMind team, they replaced this middle portion here, right, with a neural network, right, and it managed to achieve superhuman performance where it beats all the other humans playing the same game. So going by this same direction, right, you can probably see where I'm going. The job of an ATCO, air traffic controller in this case, they would also have to process complex information to arrive at an action. However, in this case, you can probably see where I'm going. You don't want to just replace the middle portion here with neural network. Right? Instead, it will be better, right, for a neural network to assist the ATCO. Right? That's what we'll be talking about in my presentation. So why deep reinforcement learning? Okay, traditional machine learning frameworks, right, learns an X to Y mapping. Right? You have an X as an input and Y as an output. In our case, it will be image as an input and action to release or not to release. Right? However, we have a huge problem, right? Because we have data on X, but we do not have data on Y, right? We don't have the labels for the data. So the solution in this case would be to actually use reinforcement learning to approximately map rewards to the action. So in this case, in the case of deep reinforcement learning, you can have X, but let's say you don't have a Y, that's okay, right? Because you can use reinforcement learning to help you approximately map these rewards to action. The downside is that you need a simulator for training, not very sample efficient. However, if you have a simulator for training, you can just train forever, provided that the simulator is accurate enough. So the proposed solution is this. First, we gather from data, right? And we transform this data into simulator coordinates. We develop the simulator, and then we can start training this reinforcement this reinforcement learning agent on this simulator, right? Until it's convergence. And then once it converges, we can evaluate the performance and the efficacy of the reinforcement learning agent on real data. Okay. And the middle portion here requires a formulation of a Markov decision process. Right? So let me just take you through what the Markov decision process is. It basically defines 4 values: your state, action, reward, and the next state. So you have an environment like this. In this case, it will be your runway, right? We'll be simulating runway 28 of the Zurich Airport in this case. And this environment outputs an image, right? In this case, in our case, it's a 64 by 200 image, right? What you can do with the image, you can feed this image to a neural network, or in this case, is our reinforcement learning agent, right? And this reinforcement learning agent can then apply an action back into the environment, right? In this case, the action that it has is cleared for takeoff and not cleared for takeoff. Basically a takeoff clearance, right? So how does it know whether or not the action taken was good or bad? And it should learn to take the correct decision the next time round by looking at the rewards, right? So these rewards will guide the behavior iteratively to a better decision in the next iteration. Okay. So the neural network structure looks like this, and we take an image as input and outputs 2 heads. And these 2 values here in the output, it should look familiar, right? It's the same diagram we have seen before. So the algorithm that we are using will be the proximal policy optimization. And using this algorithm-wise, we can iteratively and stably train this to convergence. Okay. So now that we have a Markov decision process, we have a neural network, and we have a training algorithm. Right? So let's apply this to the Zurich Airport data. So on Zurich Airport data, we'll be using directly the arrival trajectories, right, from the data. And the arrival trajectories looks like this, right? We have a zoom in version where the aircraft starts to turn into line up with the runway. And the second picture here is that you can see that the arrivals has they have different available runway exit points, right? What this means is that they have a variance in runway occupancy time, right? And this is a figure taken from the star chart of Zurich Airport, and this point here, the IRS point here, fixed point D10.3, right? That stands for 10.3 nautical miles away from the threshold, right? Is where the airplane starts to turn in. Okay, so now I talk to you about the simulator. So our simulator looks like this, right? And it generates scenario on based on this criteria here. One is that it will generate arrivals at different random intervals, right? To simulate different traffic densities. The second characteristic of our scenario generation is that real aircraft trajectories will be used, right? So that the uncertainties from the real data is preserved, right? Especially the runway occupancy time, right? You have more than 6 different exits on runway 28. So by using these real trajectories, this uncertainty will be preserved in the data. And we want to see whether or not the agent can learn from this large variety of scenarios. Okay, so our simulator has 2 screens, right? One will be shown to the agent or maybe the ATC in this case. However, screen 1 is meant more for the training of the reinforcement learning. And we have a second screen here, which will be more familiar to an ATC controller, hopefully. Is a graphical interface that shows the surrounding air traffic, right? But feel free to insert your favorite graphical representation that is familiar to an ATCO here. Over here, with just a placeholder. And okay, so screen 1, let me just explain the elements in screen 1. So screen 1 over here, you have arrival aircraft shown in magenta. Right? And you have a green aircraft. So you have the departure aircraft shown in green. Also, in front of the arrival aircraft, you have this red color box. Right? And what this red color box actually means is that it represents the departure arrival separation distance. So it's a distance separation in this case. You want to visually showcase the separation distance to the agent. And at the top of the screen is a confidence level of giving the departure aircraft a clearance. Right? And the last element on the screen here will be the wake vortex shown in blue, right, to signify the wake vortices from the previous departure aircraft. Okay, so screen one show is a bit weird, right? So actually, the more intuitive sense for everybody here would be this screen here, right, where the arrivals will just arrive, will just move from right to left, and then exit at its runway exit point. And actually, what the agent is shown is information, spatial information up to 10.3 nautical miles away from the threshold. Right? The consequence of this is that the agent can only have visual information up to 10 nautical miles from the threshold. So this is like a constraint on the agent's ability to see the surrounding information. Right? In our test, it's shown that this is enough. So, all right. So this screen is too long, right? So what I did was I cut it up, chopped it up, and I just stack them up together like this. Right? So arrival aircraft will move from box 1 to box 7, and then onto the runway, and then it exits at the runway. Okay, so next I'm going to show you a video of the train agent operating in this environment. Right? I think one thing to notice here is you should watch as the agent controls the departure clearance and avoids the different separation distances. It also takes off only after the arrival has exited the runway. So hopefully screen 2 on the right here, right, it is something familiar, more familiar to the ATCO. Okay, let's move on. Okay, so the question here given to us before was, why do we use image as an input? So if you imagine the previous time and space diagram here, it has to, whatever input that we give the agent has to represent information in time and space, right? Also, it has to somehow encode the 3 different factors, that the departure separation, the departure arrival separation, and the runway separation. Right? You want the arrivals to exit the runway before you can depart. So the input given to the agent looks something like this, right? It's a 64 by 200 image, grayscale image, and we stack 4 of these grayscale images from different time, right? So it can concisely represent information in time and space in one single image. And immediately you can see the advantage over here. So what are a few advantages here? Concisely represents spatial and spatial temporal information in one fixed sized image, right? And the second advantage here is that agent can easily represent different number of aircraft, right, without changing the size of the input vector. So it also, in this formulation, it also shown that it has acceptable computation time. In my laptop, on a very old laptop, like 2-3 years old, it can still consistently run 150 plus frames per second on the laptop. And also by using an image, right, it's an intuitive representation that is applicable for human to see as well. Okay. So how do we test the agent? So after episode has ended, right, you can have the trajectories in the time-space diagram like this, right? And what we can do with that is that we can actually back calculate, right, and we can find out how the agent actually performs, right? We can have the actual number of slots that are in between that exist in between 2 arrivals, right? And we can find the performance of the agent using the metric shown here, right? We call it the coverage metric. So for the Zurich Airport data set, right, for over 4,500 departures, we achieved 0 ground collisions, collision during takeoff or landing, right? And we also cover over 72% of the slots. So we want to also take a look over here of the agent's conformance to the different separation distances. So the first one over here would be the departure separation. So in this case, most of the time, it releases slightly below 150 seconds. 150 seconds is optimum in our case for the experiments we've shown here. By the way, we can tune this using the reward function if desired. Okay. So the next one over here will be our departure arrival separation, right? The physical meaning of this will be shown in this arrow here, right? Is the time difference between the start of the departure and the departure arrival separation, right? Previously, it was shown that departure separation is in terms of distance, right? But in this case, we converted it to time based on the approach speed. So in this case, it's shown that the agent tends to release the departure aircraft before it comes too close for comfort, right? So that's what this diagram here is showing. And the last separation distance over here is that we want to take a look at the runway separation, right? We want to make sure that it has exited the runway, the front arrival, the leading arrival aircraft exited the runway before a departure aircraft can take off. Right? In this case, it's shown that the agent can do the same. You can conform to this standard. Okay, so maybe 4,500 departures is not good enough to show the robustness of the system. So we did the exact same setup over here, this time based on Changi Airport's data, right? We achieve a similar performance. However, in this case, we increase the number of departures, right, to over 1.17 million departures. It still achieves zero collisions, right? Your collision on ground and a collision to take off and landing. Bear in mind, these are experiments based on a random arrival sequence and a random density, right? So it has a wide variety of situations to be tested on. Okay, in summary, we have demonstrated that we can train a reinforcement learning agent based on real aircraft arrival trajectories, right? It can conform to different separation, and it has almost zero. Yeah, actually it has exactly zero collisions for over 1 million departures, right? It can be used in a recommendation system for controllers in this case. Things to note, however, slotting in departures might be a trivial problem to solve based on the feedbacks from the paper reviewers, ATCOs, and the translation of simulated performance to real-life performance is not really tested here. And the behavior of the agent is very highly dependent on the formulation of the reward function, right? So, but however, over here, you can see the advantages of formulating in the Markov decision process is that you can easily and intuitively tune the reward function, right? So again, even if you have data on X, we might not have the labels, right? So deep reinforcement learning is a way to bypass the need for the labels, right? So just formulate the problem in the Markov decision process and have an accurate simulator, right? So even if we do have the labels Y, right, the trained model might not be optimal in our case, right? So which further highlights the advantage of using reinforcement learning, right? So you might remember previously AlphaGo, right? Go against Google DeepMind's algorithm. Right? It might not have been headline news if it was only trained on labeled data. Instead of a Lee Sedol, that you seen stressed out over here, you might have seen a more smiling one if it was only trained on labeled data. But that wasn't the case, unfortunately, for him. Okay, so I'm going to showcase my ongoing work. Since the reviewers have said that it might be trivial, let's increase the stakes of the problem, right? We increase the complexity of the problem, right? With multiple queues, different aircraft type, and different target takeoff time. So as you can see on the screen, the departure aircraft, they have their color slowly turn to pink in this case. So pink in this case would mean that they are late. So agent in this case would not only have to depart at the correct timing, however, it has to also make sure that it's not too late, and also has to formulate the different sequence, right? So in this case now, the different sequence is the departure separation is now sequence dependent, right? And also the balance between the penalty if the aircraft the runway threshold waits too long past its target takeoff time. Okay, I believe that's the end of my presentation. Thank you everyone for listening to me. Yeah, back to you, Prof. Samir.
Thank you so much, Lee Long. Wonderful to see these simulations and videos. We have lots of questions to the panelists. I'm glad that they have been answered. Many of them have been answered, but there are still some queries I would like to pose to the panelists. Maybe Mohammed, we can start with you. People want to know, for your upcoming live trials at Copenhagen, what are the main challenges you are facing and how you're preparing for that?
Samir, can you please repeat, because there is a lot of echo. I cannot hear your question correctly.
Okay, can you hear me now? Can you hear me now?
Yeah, now it's okay.
Okay, so for your upcoming live trial at the Copenhagen airport, what are the preparations you have made apart from taking a vaccine?
Sorry again. What are the predictions that?
What are the preparations you have made for these live trials at Copenhagen Airport?
Okay, so we held different meetings with the Copenhagen Airport operational to learn about the operations in Copenhagen Airport. We received surveillance data from them to do the analysis of the ROT analysis, such the one that Lee Long has just shown. So we progressed on the machine learning analysis of the ROT for Copenhagen, and we have already released the 2 studies on that. Now we are in the stage of preparing the software that will be used by the controller in the live trial. And we start validating or testing the software next month in Copenhagen.
Okay, wonderful. Thank you so much. Maybe with Bob, this question actually comes up in every webinar, seminar, and I think Yix from Saab NTU Joint Lab has asked this question, which you have answered, but I would like to hear more reflection about the main challenges when it comes to the adoption of the AI-based technology, especially from the regulatory perspective and certification perspective. Bob?
So first of all, it was a great question. And I don't think there is an answer yet. We work with EASA, so look at what the safety regulator in Europe would be looking at from a certification perspective. There is a working group in EUROCONTROL that's also looking at it. Certainly I attended one of their conferences before we all got locked down. And you can see quite a significant list of things that have to be thought about. So traditionally, okay, it's a new domain, but traditionally in that new domain, it looks like a very simple process of having different samples of data that you're using for either training the model or validating the model. But of course, a lot of the algorithms that are used are, let's say, black boxes. We don't really understand how they work, and therefore we can't anticipate what the results would be. So then safety becomes the main criteria. I think today we're not at a time where we could be using this in a live environment. So when we look at the possibilities of use of an AI approach, it would be very much along the lines of, for example, defining a playbook that can be used to guide people in terms of a plan. And in that case, I would give examples of being able to brief operational staff about what we think will happen tomorrow. AI is quite good in that concept. And I know that one of the major European service providers uses this on the basis of looking ahead a year, looking ahead 6 months, a month, a week, a day, to anticipate what safety issues might happen on the surface and on the runway, just on historical data. So you can brief people and have an awareness that this is a similar day to when we've had events, for example, crossing a runway in low visibility or something like that. So really much along the lines of non-safety critical, providing advice, providing information, providing planning, or more as we now start to move into the TBS world, that was described a bit better by Mohammed than my presentation. There we start to look at AI in terms of reducing the buffers. That will not be used in actual real time. It's in the buffer preparation of data that's used then by the system. And there you can use potentially more traditional ways to confirm that this is not going outside of any unexpected bounds that you could set. So I think we're quite some way from being able to answer the question that, yes, we can use AI, safety critical, real time. It's something that will be, I think, based on playing and testing and being able to get to a point where people are building their confidence in it. Li Long showed me something there, and I'm just wondering whether there are games that can be played. Okay, it's just a word that came up and I may be misinterpreted, but is there some sort of gameplay that can be done to be used as a validation for multiple scenarios, which way outpace what the human being can do? And that might be one way of testing it as far as you can go to get a percentage degree that you can say it's as safe as we can test through our system. Sure. Not a good answer, but I think that's probably where we are at the moment.
Very well reflected, Bob. It's always a pleasure to hear your deep learning thoughts on this topic. My next question is to Dr. Thin. People are wondering your data-driven machine learned simulator. Will you be able to make it open source online for people to contribute and maybe test it and can trial their own algorithms?
Thank you, Samir, for that question. Honestly, I think it's the trend right now for people working on machine learning and artificial intelligence for sharing and open source for this one. So I think that for my team, we also have the plan to publish on the code and put everything on the open source, but it's not at the right time right now because we are still on the development of the software. So I think that within this year, after we have matured the simulator, I think we will make it public for community to contribute for the surface movement problem. I think that's yes.
Yeah, that would be great. Fantastic. Now, last question is Mr. Li Long. Li Long, people have just asking about your image-based simulation approach. And they're asking how you can represent non-image data, such as target takeoff time, and how can it be represented in the states of the DRL formulation?
Okay, sure. So the target takeoff time in this case, in my current work now, will be represented in the color, right? The color gradient of the departure aircraft. So so imagine white in color, for example, would mean that it is not late. However, a black color, you slowly fade to black, right? Indicating that it's late. So this color change from white to black will indicate transition from not late to late, right? And hopefully the reinforcement learning agent will be able to balance between being late and not late and the other different problems that are thrown at it, right? So that's how it's formulated in the state.
Thank you. We have already ran out of time, and that was very fantastic feedback, lots of questions. Thank you for the panelists for answering them online. That was an amazing thing to learn from all of you. And towards the end of this symposium, I would like to thank our collaborators, CAS, Civil Aviation Authority of Singapore, for providing valuable research data. Also to our collaborators at the EUROCONTROL PRU, Rainier, for providing data for this research. And also thanks to Ms. Swan from ATMRI for providing logistics supports and administrative supports. And we look forward to all of you to join our next symposium in 3 months' time. So it's a quarterly symposium that we organize with our research collaborators. And thanks especially to Rob and Muhammad for collaborating on these projects and sharing some great insight. And we wish you all the best for your live trials. And we look forward for our collaboration and to do the same and further research in Singapore as well. A very good evening to all of you and have a great day. Bye-bye.